this Protect Open webinar. My name is Gaël Durand, and maybe you could stop. Yes, thank you. So my name is Gaël Durand. I'm coordinating the Protect project, and Protect is a ASH 2020 project funded by the European Commission, dealing with the mass balance of the land cryosphere and the impact on sea level rise on a range of timescales, from decadal to multi-centenarial, but also on a range of spatial scales, from the global mean to regional and some local implication on case studies. Today, we have the privilege to have some of the IPCC authors who strongly contributed to the content related to sea level rise in the working group 1 and 2 of the last IPCC assessment reports. They will summarize this content, and this will be followed by a summary of a policy brief, of course, in line with the IPCC consensus and published recently by Protect, Croquico, and SCORE, 3 European projects investigating sea level rise issue. So this event was planned during the COP27. Today is the occasion to open this synthesis to a wider audience, and also it will be recorded and at the disposal of anyone. How this webinar is organized, we will have 1 hour of presentation. As I just said, this presentation will be recorded. And if you have questions, please write them down in the chat. And at the end of the talks, we will stop the recording and we will do our best to organize the discussion and ask the question to the speaker for you. And this discussion will last 1 hour at a maximum. So Bob, thank you for joining us, and please share your slide, and the floor is yours.
My pleasure. Thanks, everybody. My name is Bob Kopp. I am a climate scientist and sea level scientist and professor at Rutgers University in New Jersey in the United States. And I was one of the lead authors of Chapter 9 of the Working Group 1 report of the IPCC. So we're, just by context, I'm going to speak for about 25 minutes, and then I'm going to hand it off to my colleagues from Working Group 2 to talk about impacts and adaptation. Now, I'm sure basically everybody here is very familiar with the IPCC, but just for context, the synthesis report that will be coming out early this year will conclude the IPCC 6th assessment cycle, and that 6th assessment cycle taken together, including both the 3 working group reports that came out in 2021 and 2022, as well as the 3 special reports on land, on warming of 1.5 degrees C, and oceans, cryosphere, and a changing climate. Those reports collectively constitute the most accurate and up-to-date global synthesis on changes in the Earth system, their impacts and adaptation and mitigation. Now, it's important to note, right, this is assessment. This is not original research. The goal of the IPCC, of course, is to inform governments and other decision makers about pathways and impacts. Our goal is to be policy relevant, not policy prescriptive. The 6th assessment report as a whole, the 3 working group reports, were led by 721 scientists from 90 countries. As I said, I'm going to focus on the working group 1, the physical science report, which was written with lead authors for 234 from 65 countries, and that were based the assessment on 14,000 studies analyzed over 3 years. And I do want to note, there is our sea level rise implications and reports across the 6th assessment cycle. We're focusing on the working group 1 and working group 2, but sea level was, of course, also a major focus of the ocean and cryosphere report that came out in 2019 and touched upon in the land and 1.5 degrees reports as well. So there are a few key messages that emerge from the working group 1 assessment overall. So I want to present a couple of those to you in the context of sea level change. So while I'm mostly going to talk about projections, first let's set a baseline of where we are. As the report summarizes, recent changes in the climate are widespread, they are rapid, and they are intensifying, and they are unprecedented in at least thousands of years. And that is certainly true on the sea level side. So this figure here on the left is showing you from both geological data in pink and instrumental data at the end here, estimates of global average sea level over the last 2,500 years. And the assessment of the report is based on literature over the last century. Sea level has risen more than in any preceding century and at least the last 3,000 years. If we zoom in for the last 170 years, you can see here several different estimates of global sea level from instrumental data, and they consistently show that global sea level has been rising at an accelerating rate since at least the 1960s. In particular, the rate of rise since 2006, which is about 3.7 millimeters per year, is nearly 3 times that over the first 7 decades of the 20th century, about 1.3 millimeters per year. And of course, at a global scale, the processes driving the sea level change, the sea level budget, can be counted on a couple of fingers, right? It is mass loss from the ice sheets and glaciers. It is warming of the oceans, and there is a small contributor from the changes in the amount of water stored on land. But when we start looking at a regional scale where the impacts occur, there are many more processes that we have to think about. And so, as I will get to later, when we start thinking about changes in the circulation of the ocean and atmosphere, when we start thinking about the way changes in the cryosphere and where water is stored on land affect the Earth's gravitational pull, affect the Earth's rotation, all of these give rise to sort of a complicated story that we have to think about when we're interpreting local records and think about when we're projecting future changes. But at a global scale, as I mentioned, right, the basic story is that heating of the climate system has caused sea level rise through ice loss on land and thermal expansion from ocean warming. The sea level budget is pretty close to closed. And this is a summary of the contributions since 1971, where each of these boxes represents 1 centimeter of sea level rise. So these 5 boxes here represent the expansion of the ocean as it warms. These 2 boxes here represent the contribution from mountain glaciers, Greenland contribution, the Antarctic contribution, and this is a contribution here from changes in water stored on land, particularly that associated with groundwater withdrawal. The report also assesses the literature on the attribution of both sea level as a whole and each of these individual components, leading us to conclude that it is very likely that the main driver of global mean sea level rise since at least 1971 has been the human effects on climate. What's more, right, this is a nearly about almost 50-year average of contributions, but the ice sheet contribution in particular is growing pretty rapidly, from about 1/10 of a millimeter per year over the 1990s to about 1.1 millimeters per year over the last decade. At a regional scale, a variety of factors complicate the sea level rise picture. So as I mentioned, changes in oceans, winds, and currents, which exhibit a lot of natural variability, as well as potentially changing in response to the warming planet. There are gravitational effects of moving water and ice, and there's also sinking and rising of the land due to both natural and human factors. And this figure illustrates some of that. So this map here on the left, these are trends in the height of the sea surface from 1992 to 2021. And you can see some areas experiencing sea level rise much faster than the global average, say in the Western Pacific, and other areas, for instance, the Eastern Pacific coast of North America, experiencing much less sea level rise than the global average. So that's one of the terms. And then the sinking of the land also has a lot to do, in fact, is the primary driver in the places in the world that are experiencing the fastest rates of relative sea level rise. And you can see these sort of long-term land subsidence contribution here. So places like Greater Manila, places like the Western Gulf of Mexico are experiencing especially fast rates of subsidence that are leading to especially fast rates of relative sea level rise. And we are already seeing impacts from these changes. So higher sea levels are leading to more frequent and extensive flooding. So here we have photos of high tide flooding, both in the Philippines and in the United States. Globally, if we look at the entire global data set of tide gauge data, high tide flooding was more than 60% more frequent over 1995 to 2014 than over 1960 to 1980 as a result of rising local sea levels. So that's where we are. Looking forward, many changes to the ocean's ice sheets and sea level will be irreversible for millennia. They're locked in place. But by reducing greenhouse gases, these changes could be slowed and their ultimate scale reduced. So over here on the left, we are showing you the report's projections of sea level rise under a variety of different emission scenarios, ranging from a very low emission scenario consistent with limiting warming to 1.5 degrees C to a very high emission scenario consistent with sort of a reversion to the rapid rate of fossil fuel consumption growth seen in the 90s and the 2000s. And then I will get to this curve, the low likelihood, high impact one later. What all of these analyses show is that regardless of emission scenario, sea level is going to continue to rise for many centuries to come, creating an escalating hazard for coastal communities. Relative sea level rise will increase the frequency and severity of coastal flooding and coastal erosion. And as a consequence, a vast majority of the world's regions are projected to experience an increase in coastal flooding throughout the 21st century. Now, through the middle of this century to about 2050, sea level projections exhibit limited sensitivity to emissions. You can see the rather limited spread here. Relative to the baseline in 1995 to 2014, global mean sea level rise by 2050 is likely to be about 15 to 30 centimeters, regardless of emissions reductions. The differences among the emission scenarios are in the order of a small number of centimeters. And as a consequence, extreme sea levels that occurred once per century in the recent past will occur about 20 to 30 times more frequently by 2050 on average around the world. Now, beyond 2050, sea level projections are increasingly sensitive to those differences between emission scenarios. So if we look at a high emission scenario, one sort of consistent with around, say, 3.5 degrees of warming, by 2100, the likely global mean sea level rise is about 60 to 90 centimeters, whereas under a scenario consistent with limiting warmings to below 2 degrees C, we're looking at about 30 to 60 centimeters of global mean sea level rise in the likely range. By 2150, these differences grow to about 1 to 2 meters under the high emission scenarios, about 0.5 meter to 1 meter under the low emission scenario. What's more, all of these likely range projections the IPCC presents are focused on the processes in which there is the most degree of agreement among different research. So what we would call in the report the medium confidence processes, or medium or high confidence processes. So those likely ranges do not include the potential for processes in which there is currently limited agreement among different researchers and among different models on how fast they will proceed to drive up the rate of sea level rise. But those processes are potentially quite important. So we did also consider those. The overarching conclusion from looking at those, from trying to consider these low confidence processes based on the limited amount of literature available, is that the more we limit our emissions, the lower the chance we trigger instabilities in the polar ice sheets that could substantially increase sea level rise. If you think about, so step back broadly, we had a full range of literature available for those 5 emission scenarios, considering the processes in which the models agreed. We had only a low emission scenario and a very high emission scenario where we had a little bit of evidence in the literature where we could think about these processes like marine ice cliff instability or faster than expected marine ice sheet instability that are still quite contentious. But the conclusion from looking at that is that global mean sea level rise well above the likely range, approaching 2 meters by 2100 and 5 meters by 2150 under a very high greenhouse gas emission scenario, cannot be ruled out. Now, it appears based on the assessment we've done so far that these processes are probably not that important under the low emission scenario that's consistent with limiting warming to 2 degrees C, but there wasn't really a literature place to look in between the low emission scenario and the very high emission scenario. Higher global mean sea level rise before 2100 could be caused by a number of things, including earlier than projected disintegration of marine ice shelves that help to hold back the ice sheet, particularly in Antarctica, and the abrupt widespread onset of marine ice sheet instability and or marine ice cliff instability in the Antarctic, as well as faster than projected changes in melt from Greenland and runoff from Greenland. In the longer term, looking at the multi-thousand year timescale, sea level is committed to rise for centuries to millennia, even under a very low emissions scenario. So this plot here over on the right, it is showing you a few things. So on the x-axis here, the horizontal axis, is the peak global surface temperature attained before the warming starts to decline. And the different colors here are representing the warming level based projections on a 100-year timescale, on a 2,000-year timescale, and a 10,000-year timescale for warming of 1.5 degrees, 2 degrees, 3 degrees, 4 degrees, and 5 degrees. Also compared to temperature and sea level during the last interglacial, 125,000 years ago, and the mid-Pliocene warm period, about 3 million years ago. And so the punchline is that over the next 2,000 years, global mean sea level will rise by about 2 to 3 meters if warming peaks at 1.5 degrees C, by about 2 to 6 meters if warming peaks at 2 degrees C, 4 to 10 meters at 3 degrees C, 12 to 16 meters at 4 degrees C, and 19 to 22 meters if warming is limited to 5 degrees C. And the rise will continue after for several millennia. So this is a visualization of what that means. The fact that in the longer term, sea level is committed to rise for centuries to millennia. This is a picture of the Abu Abbas al-Mursi Mosque in Alexandria, Egypt, a visualization from Climate Central, showing the difference between that 2 to 3 meters associated with 1.5 degrees warming and the 2,000-year commitment associated with 3 degrees of warming. So although there are multiple meters of sea level rise in the pipeline, even under a 1.5 degrees C world, limiting emissions slows sea level rise and allows more time for adaptation. One of the new framings the report introduces is thinking about uncertainty in sea level rise has a function of when different thresholds are going to be crossed rather than if they are going to be crossed. So, for example, this figure here over on the right is asking the question under different emission scenarios ranging from the very low to the very high, and also these lightly colored areas, I think, including those low confidence processes. When is global average sea level rise likely going to exceed 0.5 meter? And we can see that that's likely between about 2080 to 2170 under low emissions, or as soon as 2070 to 2090 under very high emissions. Similarly, if we look at the 1 meter threshold, that's likely to be exceeded between about 2150 and some point after 2300 under low emissions, whereas under very high emissions between about 2100 to 2150. And if we consider those low confidence processes, the ones where there's limited agreement in the literature, At the 83rd percentile of those projections, under very high emissions, we could be looking at 1 meter exceeded as soon as 2080 and 2 meters exceeded as soon as about 2110. Now, all of those results that I showed are in terms of global average sea level rise. But one of the innovations in this report is that we not only produced relative sea level projections for everywhere in the world, but we also put some amount of effort through a partnership with the NASA sea level change team on making sure those local relative sea level projections in the same sorts of framings you see for global average sea level in the main report are readily available to practitioners around the world. So if you go to sealevel.nasa.gov/IPCC, it'll bring you to the sea level projection tool website, where you can go into any grid cell or any tide gauge in the database and pull up figures that look analogous to those for global average sea level that I showed. So here, for example, is relative sea level projections for Alexandria, Egypt, under a low emission scenario, high emission scenario, and a very high emission scenario that considers those low confidence processes, as well as the question of when under these different scenarios and either considering low confidence processes or not, the 1 meter threshold is exceeded locally. I want to conclude by taking my IPCC hat off for just 1 minute, which I did not do at Kopp, but since this is a different venue, I will, and sort of make the transition to Working Group 2 by raising the question, look, that one of the key findings in the IPCC report in Working Group 1 is that there is deep uncertainty around some of these processes that have the potential to drive these high-end sea level rise. You know, those are not things you certainly, from a risk perspective, want to treat as a certainty, but neither are they things you want to ignore. And as you'll hear from Working Group 2, that implies something about the nature of adaptation. I don't want to steal their thunder, but I do want to advertise this project that I and collaborators at 12 other institutions in the United States are working on that has some analogies, I think, to what Protect is doing, called the Megalopolitan Coastal Transformation Hub at coastalhub.org, where we are working to understand the feedbacks among changing coastal hazards, landforms, and human decisions in a densely settled urban region, specifically the region covering Philadelphia, New Jersey, and New York City, and use that understanding of feedbacks to support flexible, equitable, and robust long-term planning to manage climate risk. And I'm happy to talk more about that with anybody who's interested. And with that, I can conclude the Working Group 1 part of the report and hand it off to my colleagues from Working Group 2.
Thank you very much, Bob, for this very clear presentation. So I'm going to share now the presentation of Working Group 2. Can you see my screen? And it's not the presentation mode, right?
No, it's perfect, Gonéri.
Perfect. Okay, thank you. So I will start and then leave the floor to Marjolijn and Haasnoot from Delta S. So basically, you can see from Bob's presentation that we are just at the beginning of a new era where sea level is going to rise for centuries, and this will be a major change for coastal area. So Working Group 2 is assessing the impact of these events, the vulnerability of coastal area, and adaptation, of course, for many topics, but including for coastal zones. And here what we did was to identify the key messages from the summary for policymakers, mostly, that relate to sea level rise. Because you can find in the IPCC report Working Group 2 many chapters that deal with sea level rise. The first one is the cross-chapter paper 2 about coastal and settlements by the sea. So this is what Marjolijn contributed to. And another one is a section in the ocean chapter number 3 about sea level rise. And all the regional reports about Europe, North America, South Africa, and Asia also deal with sea level rise. So this presentation has been prepared by many co-authors, and I will leave the floor to Marjolijn to present the first slides on this.
Yeah, thank you, Gonéri. Well, we find that sea level rise will affect coastal sediments and infrastructure and coastal ecosystems. And one of the findings is that globally, the population that is potentially exposed to a 1 in 100-year coastal flood is projected to increase by about 20% if global mean sea level rises with about 15 centimeters relative to the 2020 levels. And this exposed population doubles at about 75 centimeters of sea level rise and triples at about 1.4 meter of sea level rise, assuming that the population will not change and without additional adaptation. So if you compare that to the working group 1 results, this amount of population at risk will happen at some point in the future. So the figure that you see here presents the projected number of people at risk to a 1 in 100-year coastal flood for the SSP2 4.5 scenario from working group 1. And the size of the circles indicates the amount of people at risk, and the color indicates when in time this may occur. And then the left part of the circle is the absolute amount, and the right part of the circle is the percentage of the region. And what you see here is that in particular in Asia and also in West Africa, but also in parts of Europe, the population at risk really increases. And not only at the end of the century, but also in the next 20 to 40 years, which is also indicated by this 20% increase with already 15 centimeters of sea level rise. So this, this has a large impact on these coastal regions. Next slide. So sea level rise poses a very distinctive and severe adaptation challenge. And this is because there is this slow onset of changes, and these escalate in the coming decades. And these impacts are an increase in the frequency and the magnitude of extreme sea level events, which you see also here in this figure. So the left part is like the current situation where you have the mean sea level, and then the extreme events for like once a month or 1 in 100 years. And with sea level rise, not only the mean sea level increases, but also these extreme events increases. So, for example, a 1 in 100-year event may occur yearly when sea level rises. So this is a special challenge for adaptation. And not only this slow onset and escalating impacts, but also this large uncertainty that Bob already talked about, in particular when there is this low likelihood, high impact outcomes associated with the collapsing of the ice sheets. But fortunately, there's a lot of adaptation options that are available, and adaptation has already reduced impacts. So responses to sea level rise and land subsidence include protection, either through nature-based solutions, like with wetlands, for example, or hard protection with storm surge barriers. They also include accommodation, where you have like elevated houses, for example, or floating houses. And then there is advancing, when there's building a new coastline, where you can, for example, put new developments, and this coastline can be higher. And there's, of course, also planned relocation, planned retreat, in order to move from risky places. And then another option is to avoid all these impacts of sea level rise by preventing new developments in exposed coastal location. And all these responses, the ones that were just mentioned, they are mostly physical, but of course they need to be supported by institutional measures and governance measures. They are more effective if they are combined, sequenced, and especially planned well ahead, taking into account these long-term adaptation needs that Bob already presented, like the committed sea level rise that we face. And not only that, if they are aligned with socio-cultural values and development priorities and underpinned by inclusive community engagement processes and the socioeconomic developments. And here at the bottom, you see some examples of, for example, accommodation on the left, the storm surge barriers in the middle, and the nature-based adaptation with wetlands at the coast. So this combination of adaptation, you can map these in what we call adaptation pathways. And by mapping these different sequences of adaptation options, this can help you to identify lock-in situations and also map the full solution space that may be needed if we are not able to mitigate climate change. But you also see that choices in the near term can determine the long-term adaptation options. For example, avoiding developments in risky places also may make the solution space in the longer term larger, because there's also more space for these for some of the adaptation options. And in some cases, we also call this maladaptation, when adaptation increases risk or results in these lock-in situations. For example, seawalls can effectively reduce impacts to people and assets in the short term, but they can also attract more people in a certain area and then result in a lock-in situation and increased exposure, where it becomes more difficult to adapt if it is not integrated into a long-term adaptive plan. And exploring these different sequences of adaptation can help to avoid this lock-in situation. I give the floor to you, Gonéri.
Thank you, Marjolijn. So I will go on. So one of the most urgent challenges that is identified on the question of sea level rise adaptation is chronic flooding at high tide. So it's an event that only emerges because sea level rise is superimposed with tides and with natural variability of sea levels. And what you observe on the ground is at the beginning, just a few days where sea levels are flooding some low-lying areas, but this increases over time as sea level is rising. The best examples that we have on this in Europe is Venice, where these aqua alta have increased consistently with sea level rise since the middle of the 20th century. But we have also a lot of feedback from the US, from the eastern coast of the US, where sea levels are exacerbated by ground subsidence. So, for example, in Virginia. And the report that we get from this area where chronic flooding is increasing earlier than in others is that it is difficult to manage, meaning that a lot of ports are experience lower availability than before, just because of these high tide events. So it has an economic cost. And the response to this can take time to be implemented. And for example, in the chapter on Europe, we have the example of Venice, where now you have a barrier closing the lagoon from the sea when sea levels are too high and could cause high tide flooding. But this means also closing the traffic of ships. This took 40 years to be implemented. So now we should think about the infrastructure that will be needed by the mid of the 21st century. This is why we think we will read, right, in the IPCC report that a most urgent adaptation challenge is chronic flooding at high tide. Then the IPCC report also put emphasis on nature-based solutions, and in particular because coastal wetlands protect against coastal erosion and flooding associated to storm and sea level rise. But to implement this type of nature-based solution, you need a sufficient space and adequate habitats. And also there are limits to this adaptation, which means that until if some specific sea level rise rates are exceeded, natural adaptive capacity to build sediment will be probably reduced a lot. And for example, we have several examples here of a nature-based solution. One is dune restoration, another one is Posidonia banks in the Mediterranean, where you leave these Posidonia banks on the beach to prevent erosion. And also there is here a scheme from the chapter on small island, where you see that in healthy ecosystems, like corals, mangrove, etc., can prevent erosion and flooding or limit erosion and flooding. But if they are degraded, if, for example, waters are too warm, the ecosystem services given by reefs and by coral reefs and by mangroves will be slightly reduced and maybe even dropped. So on the other hand, the question of engineering adaptation is raising another question, which is the damages that it may cause to coastal ecosystem if it's not managed adequately. And so the IPCC says that considering biodiversity and autonomous adaptation in long-term planning reduces risks of maladaptation, and that hard defenses against flooding reduce space for natural processes, degrade, replace, or fragment ecosystems, reduce their resilience to climate change, reduce their ability to provide ecosystem services. And it is even stated in the summary for policymakers that this is a severe form of maladaptation for ecosystems. And obviously, it will not be possible everywhere to implement nature-based solutions, but there are many places where it would be possible to do so, and it may be even on the long term associated with lower costs. So basically here you see picture like it's in Guadeloupe, where the beach has been completely disappeared because you have rocks instead of them. On the long term, the IPCC also identifies these challenges related to matters of sea level rise. First, for communities living in low-lying coastal area, you have a picture here showing an area in Southeast Asia, probably flooded during heavy rainfall or an. Can you close your microphone, please? Thank you. And it may be an area with a subsidence. It is an existential threat for small island states, and you have here an image of Malé in the Maldives. It's also a concern for long-living infrastructure like energy, transport, ports, and coastal cities, for the cultural heritage, with the example of Venice, for example, for landfills and polluted soils, and for unique coastal ecosystems. And we have to keep in mind that such adaptation challenges to matters of sea level rise would occur much earlier under high rate of sea level rise, in particular if low likelihood, high impact outcomes associated with collapsing of ice sheets occur. We know that from the evidence that we have from the literature, that adaptation capacity and governance to manage risks from projected sea level rise typically require decades to implement and to institutionalize. And this is illustrated here with examples of coastal adaptation measures, from ecosystem-based solutions to planned relocation. So there are two measures which take a lot of time to implement and to plan and even to design. These are the planned relocation and the barriers, the estuarine barriers that you can see, for example, in London or in the Netherlands. This can take 50 years to implement. This means that if you want to be ready for sea level rise by the middle of this century, we should be starting now to think about the adaptation strategies. And in many places, we have to acknowledge that we are developing coastal lands without considering sea level rise. So the future of coasts depends on immediate mitigation and adaptation actions. So mitigation to limit sea level rise rates, as shown by Bob in the earlier presentation, to give time to adaptation and to preserve resilient ecosystems. And adaptation to committed impacts of sea level rise, like flooding, erosion, and salinization. We have also to take in mind that while implementing climate policies, we can create more resilient coastal environments. And in the IPCC report, you can see in the lower figure how the co-benefits of adaptation are assessed. This is a figure from the summary for policymakers. And one highlights the strategy consisting in raising engineering coastal defenses. It is obviously very efficient to protect against sea level rise, but it has adverse impact to ecosystem, and it has also not a lot of co-benefits across the sustainable development goals. If you look at a broader integrated coastal management that considers also ecosystem services and social aspects, then you can have, in the best case, a lot of co-benefits across the sustainable development goals, like reducing poverty, etc., etc. So thank you for your attention. I will leave the floor now to Robert Nicholls, who has been contributing author for the 6th assessment report and lead author for previous assessment report and even coordinator actually. And he will present the policy brief that Gaël mentioned at the beginning of this event.
Okay, thank you then, Gonéri. So yes, so this is a policy brief produced by 3 EU projects, SCORE, Coquelicot, and Protect, and it follows on very much from the previous 2 presentations in terms of recognizing that sea level rise is inevitable, as we've heard already, and framing that around, you know, it's a matter not of it's not a matter of if sea level will rise by 2 meters, but when it might occur. And I suppose our goal here is to really change people's thinking, because if you go back a long time, sea level used to be a datum. You know, they used to record mean sea level might be measured for a lunar nodal cycle to define a national datum. That happened in the UK in the Victorian period. I think around most, certainly in the US, I think datums, that's no longer the case. But that mindset that sea level is something fixed, we need to really change people's minds and start to get them to think through what the real implications are of this. So this picture here really is building on one of the images that Bob Kopp showed, which is really showing with different emission scenarios when might we see a 2 meter rise in sea level. And you know, so with the high emissions could be as early as the end of this century with ice sheet collapse, up to sort of up to maybe sort of much longer millennia scales with lower emissions. But it's still inevitable, and we still need to be doing that planning, as Gonéri has said, really to start thinking through what this really means. Next slide, please. And so this second picture really is, well, what do we do about the fact that sea level will rise 2 meters? And here it's not one thing, it's clearly a process. So coastal adaptation is essential in addition to mitigation. And this process is, first of all, you know, sort of there's 5 steps here: prepare the ground for adaptation, look at the risks and the vulnerabilities, assess the adaptation responses, think about implementation, and number 5, monitor. So most of the time, maybe you're monitoring what you've done, but it's a process. And after, you'll do something that will work for a while, and at some point you'll decide we'll need to do more. And that could be because sea level's risen more. It might be that society's changed. I mean, there are other drivers of what we do in this wheel, as well as societal preferences, etc., and climate services that can support this. So I think it's important to sort of recognize the choices we face and to also see that there's a series of pathways that we might follow, as Marjolijn was sort of showing, and to sort of start to build these into our thinking about the future of the coast, so that we choose the coast we have, rather than just kind of get in an ad hoc way into a situation we didn't anticipate and don't want. So with that, I'll pass back to Gonéri. Thank you.
Thank you, Robert. And I think we are now to the, we can handle questions. And I think the Protect Bureau will handle question now.
Yes, maybe you could stop sharing, Gonéri. Thank you. Thank you, the four of you, for this very clear presentation. Very few questions at this stage, mainly regarding the material presented here. So as I mentioned at the beginning, it is currently recorded, and we will publish the video. And also, if the speakers agree, we will gather their slide all together, and we will publish this on the Protect website. And I guess we also have the mailing list, so this can published. We can keep you informed on the fact that it has been published and is available. And no, there is no certificate for this webinar. There is just one question rising now, and what caused sea level rise on the Earth's surface to be different in different regions? Bob, maybe you want to answer.
Sure. Well, there are lots of different processes. I mean, honestly, one question you might ask is actually why might it rise the same everywhere if you think about it, right? But let's go back to actually let me pull up the slide I had on that. So there are a few things. Go to the slide. There are a few things. So one are what we consider sort of ocean and atmosphere dynamics. So simply think about winds blowing ocean water around, or think about currents moving ocean water around, right? That will lead the sea level to shift. Winds blowing, say, from the east to the west will reduce sea level in the east and increase it in the west. And that will, occur both potentially long-term changes as the climate changes, but also in terms of natural variability happening on a variety of timescales from days to decades. There's also, when you move, think about the contribution from the ice sheets or glaciers, or even from land water storage, when you move masses around, you're talking about huge masses, right? To raise global sea level by 1 millimeter requires moving about 360 billion tons of water from ice into the ocean. And when you move masses of that scale around, it changes the planet's gravitational field. So for instance, if you had this massive ice in Greenland, and then you melt it and that water gets distributed in the ocean, you will actually reduce the gravitational pull of Greenland. And so you will get a sea level fall near Greenland, even though you get a sea level rise globally. It also affects the Earth's rotation, which has important effects, but similar. And then the other thing is, when we talk about sea level rise locally, usually we are talking about relative sea level rise, because that's what matters for coastal flooding, right? And the relative sea level rise is the difference between the height of the land and the height of the sea surface. And there's a variety of processes that can cause the height of the land to change. Plate tectonics can cause the land to move up or down. The sinking of the land can occur both due to natural processes. So where I'm sitting in New Jersey in the mid-Atlantic United States, the land is sinking in part because there used to be a giant ice sheet to our north. It can also happen from human-caused processes. It's also sinking along the coast of New Jersey because we pump groundwater out of reservoirs, and when you remove the groundwater, the land compresses. It can also sink because you're building construction on land. And so where you see the fastest rates of relative sea level rise in the world, places like Western Gulf of Mexico or Manila, or Bangladesh, that sinking of the land has a lot to do with it.
Thank you. There is another question. There is other question, not in the order they appear in the chat, but I will try to ask most of the question, all the question if I can. So can you comment the reason why you present the result referring to low confidence, low evidence limited agreement, or even less? Robert, Marjolijn, maybe?
Yeah. I think we'll do it in that order. So I'll give the working group 1 answer, and then Marjolijn can give the working group 2 answer. Although the answer actually has to do more with the working group 2, which is if you are thinking about risks, it is not safe to consider only those processes in which we have the greatest degree of confidence. So, if there is a dragon lurking in the city beyond the spotlight, and you're only looking under the spotlight, you might not see it, but you really want to go look for that. We tried in the working group 1 report, something that has been tried in a variety of different approaches in past reports. How do you communicate the fact that there are processes that are well represented in models for which we have some medium or high confidence, and processes that we think might be important but are not? This has been a concern in the sea level projection literature dating back to the late 1970s. This is, the fact that ice sheets could contribute considerably more to sea level rise than what we have greatest confidence in our ability to project is something that is as old as modern scientific sea level projections. Up until working group 4, up until the 4th assessment report in 2007, IPCC generally just ignored those. The 4th assessment report, recognizing that these were important but hard to quantify, tried an approach where they said, okay, here's the sum of the things we have some confidence in our ability to quantify, but there are these other things, and so we're actually not going to give you a total projection at all, because we think the fact that there are these other processes means we can't really give you a total assessment, and that caused a lot of confusion. And so the 5th assessment report tried something different, where they added up the medium confidence projections and then had in the text below the table footnotes that said, basically you could get several tens of centimeters more because of these processes that we have difficulty quantifying. And yet you still see those projections often being ignored by users. And so we tried in this report a new approach where we say, okay, well, in all of our tables and figures, we are going to show you a quantitative assessment of what the literature suggests is plausible, if you incorporate these, while flagging them as low confidence, recognizing that, they are not things in which there is currently agreement. So the bottom line is they're important from a risk perspective. We're trying to make sure they don't get lost this time by users. And I'm going to try to hand it over to Marjolijn to give a sort of user or adaptation perspective.
Yeah, so from an adaptation perspective, I think one of the important sentences of working group 1 is that it cannot be ruled out. So it's a low likelihood, but very high impact, a future that for adaptation you would like to consider. Of course, you would like to not only consider that a potential future, but consider a range of futures. And for people who are interested, there's in chapter 17, there's a cross-chapter box on deep uncertainty, which discusses different approaches to deal with this severe or deep uncertainty. And I think in particular, this high scenario can be a game changer for adaptation, not only because of the amount of sea level rise, but also because of the rate of sea level rise. And as Gonéri already showed, that in particular for some adaptation measures, it can take decades to design them, to really implement them. And they often also have a very long lifetime. So some measures can be have a short lifetime and can be implemented very quickly. So then you can quickly, have an adaptive plan and adapt over time. But many measures have a very long, almost heritage into the future, not only in terms of the measure itself, but also because society responds to these adaptation measures. And in these circumstances, you want to, or at least consider and anticipate what could happen if we have this 2 meter and in 2100 and 5 meter in 2150, and what does this mean for the near term? Are there already preparatory measures? Do we need to research? And ideally, every investment that you take now can be like a stepping stone towards this longer term future. As there's also from working group 1, we learned that 2 to 3 meters of sea level rise will happen in the end, even if we achieve the Paris Agreement and if warming peaks at 1.5 degrees. So this, the large uncertainty, the high impacts, and the time we need for adaptation and making it like a stepping stone towards this long-term adaptation commitment is, I think, very important reason to consider it also in adaptation. I think Robert probably has to wants to add to that.
Okay. Well, thank you. I think I just reinforce what Marjolijn said. Really, I think what I'd call the high-end numbers. I think it's very important to consider the tail of what might happen. And I think of like the Thames Barrier, where the Thames Barrier, they've spent £15 million thinking about how they will deal with sea level rise. So that's quite a large investment. And again, it's a pathways approach. And in that case, they called it the H++. This is predating the AR6. This is quite a long time predating. But the idea of having this was a 2 meter rise by 2100, and could they adapt? So by having those high-end numbers, you can think through these cases, and as Marjolijn says, you're not going to be so surprised if things don't perform as you expect, and you have some sense of what you can actually do about them. So I think it's very important to avoid maladaptation to think about these high-end numbers.
Thank you. There is one question, and you started to elaborate, Bob, on that. It's what are the differences of the RR6 sea level projection and the RR5 projections?
Sure. So, I mean, methodologically, basically everything has been updated. And that goes to well, there's a new generation of climate models, so even the emission scenarios are different between AR5 and AR6. Quantitatively, the differences are, the bottom line differences are actually fairly small if you limit yourself to looking at these medium confident likely range projections. If you, sorry, I'm just trying to pull up my comparison. So if you look at, so if you look at the low emission scenario, which is RCP 2.6 in the 5th assessment report, and SSCP 2.6 in the 6th assessment report, the median projection for 2100 is 41 centimeters in the 5th assessment report and 44 centimeters in the 6th assessment report. If you look at the very high emissions projection, the median for the medium confidence projections is 71 centimeters in the 5th assessment report. It was 81 centimeters in the special report on oceans, cryosphere, and sea level change. And the 6th assessment report, bottom line is actually in between at 77 centimeters. And the difference is that basically the special report updated the Antarctic projections, but not the rest of it, and the 6th assessment report updated the whole thing. So from a methodological perspective, everything has been updated, things are up to date. If you look at individual components, you can, we could walk through the differences, but the bottom line projections, considering only medium confidence processes, have not changed that much. A more fundamental issue is, that based on, 8 years of feedback from people trying to use the report, we have tried to make sure that the discussion of these low confidence processes is made more transparent and easier for end users to access.
Thank you. Another question, how do you appreciate sea level rise projection for Africa Eastern Atlantic coast, considering the very limited availability of in situ data?
Yeah, so by and large, the sea level rise projections are driven by global scale processes. So melting of ice sheets, melting of glaciers, uptake of heat by the ocean, plus ocean dynamics, so the way the ocean and the atmosphere changes, which is something that is modeled with global climate models. And so the only bit of that is actually sensitive to the limited availability of in situ data is land motion. And in that case, you do have some larger uncertainties associated with land motion in areas where there are sparser tide gauges. But the global scale factors, you can project for the African coast based on the same physics that are in either your model of Earth's gravitation or your model of ocean and atmospheric change.
Okay, thank you. 3 questions in one. Could you please share some cases of countries, regions, cities that are positive examples of adaptation to sea level rise? In particular, those who are proactively anticipating sea level rise through ecosystem-based adaptation, and what can we learn from the challenges they are facing and overcoming? Who wish to answer?
Maybe I can start. And I think the first point is that we observe a lot of coastal adaptation across the world. And we even observe some adaptation that anticipates future rates of sea level rise. And for example, we have this box on Venice in the European chapter, which shows that this barrier that has been built is anticipating sea level rise, has been anticipating sea level rise, and it has anticipated that until by 50 centimeters of sea level rise, the barrier should be closed 2 months per year, which is a lot, which means that ships cannot enter in the lagoon, which means a lot of damages to coastal ecosystem. So we observe a lot of coastal adaptation, but we also observe that there is no example of coastal adaptation that considers all the issues related to sea level rise. So some are considering flooding during storms, others are considering chronic flooding at high tide, others considering the very long-term issue of, for example, landfills being flooded or eroded. But we have not seen a single adaptation strategies that covers all issues. And on the topic of coastal ecosystems, ecosystem-based solutions, I think that we have different levels of nature-based solutions that can be presented. And some are really consisting in restoring ecosystem in order to limit, for example, the peak water levels during a storm by restoring wetlands and things like this, or allowing dunes to accumulate sand, or for example, leaving Posidonia banks on beaches to prevent erosion. But these adaptation options have a specific limit when you exceed a particular rate of sea level rise. And this is a matter of concern, and also a motivation for one of the motivation for limiting climate change at 1.5 or 2 degrees of global warming. Yes. And if I had to select another, so there is a particular nature-based solution, which Marjolijn, I think, would be best to explain, which is taking place in the Netherlands, so the sun motor.
Do you want me to explain?
No, but just explaining well the principle and.
Oh, okay. Yeah. So the sand motor or sand engine is like they consider they work more with the natural processes. So instead of putting sand on the beaches to maintain the coast and let it grow with sea level rise, they put a large amount of sand near the beach, and then the water actually distributes the sand along the coast. And so instead of putting it everywhere, it's only in one place, and then nature kind of helps us with adaptation. Should I add more? Like, I think in the Europe chapter, there's several examples also on adaptation and experience for anticipating also the largely uncertain sea level rise. We made this inventory of how countries in Europe prepare for sea level rise, and there's large variety, which can also results in the end in inequalities in even within the region of Europe. And then I think in the cross-chapter paper on cities and settlements by the sea, there's in the annex, there's a large table with a huge amount of examples of how cities prepare for sea level rise, which I think is interesting. And then in particular for these highly uncertain sea level rise, and including this high-end sea level rise, the UK example of the Thames that Robert already mentioned, might be interesting to look at, where we, which is also applied in the Netherlands and in New Zealand, for example, where we had this adaptive approach of short-term actions and long-term options, and then also consider the path dependencies of decisions now. So each decision that you take should build up until a potentially higher amount of sea level rise, and then depending on how the future unfolds, you try to implement these measures.
Okay, thank you.
If I can just come in,
yes,
come in, Gaël? Yeah, I was going to just say, I think in terms of adaptation, I think probably the Netherlands and the UK, and maybe to some extent Belgium, are the best examples of forward thinking at the moment, I would say, although they do tend to present, they tend to, using nature-based, I think nature-based solutions as conceptualized are still quite experimental in many cases. So I think it's quite hard to judge them. And the beach nourishment examples that have been mentioned, the sand motor, are good examples. And it's worth noting that, for example, in the Dutch case, the Dutch coast has not eroded since 1990. Why? Because they pump enough sand to stop it. So that's it's a full-scale national response to coastal erosion due to sea level rise and lack of sediment. So that's an interesting case where it shows what you can do. I'll stop there, Gaël.
Thank you. But as you are speaking, maybe you can answer one question, a precision regarding the policy brief. It's IPCC considered plus 2.5 meter by 2100, but Robert Nicholls' presentation seems to consider only less than 2 meters. Why not consider scenarios?
Well, I mean, I thought it was consistent with the IPCC. We actually got the first part of the policy brief from Amy Slangen, who's on the call, who maybe would like to, maybe she can actually comment if she would like. I'm putting her on the spot a bit there, as she's probably just thinking she's going to listen. But that is material taken directly from the IPCC AR6 report, and it's looking at the regional patterns of sea level rise. So if you look at the map in detail, it's not a global response. It's actually it's giving you the different regions of the world and when sea level will reach 2 meters, the timing in different parts of the world. So as far as I understand, it is consistent with the IPCC, and Amy's welcome to respond if she would like, but maybe she doesn't wish to.
Yeah, these are consistent with the IPCC. Yeah, so we've gone through the IPCC AR6 projections and selected those times when each hits the 2 meter mark, basically. So they are fully consistent with the IPCC. There's really no difference at all, basically, between the policy brief and the IPCC AR6.
Maybe Amy was not planning on chiming in here. I'll just expand on, because maybe I miscommunicated something. So by 2100, the upper end of the likely range for medium confidence projections, the highest one, not considering these ice sheet instabilities, for a very high emission scenario, which we are not on, gets to about 1 meter. When you start considering, well, what if we were on a very high emissions trajectory and these low confidence processes come into play, what we find is that all the available sources in the literature, of which really we're drawing on 2 primary resources, agree there is less than a 17% chance, even under those circumstances, of exceeding 1.6 meters, and a less than 5% chance of exceeding 2.3 meters by 2100. So in terms of the 2100 number, I think even the sources that are more pessimistic get a quite low probability, even under a very high emission scenario, of exceeding 2 meters. The caveat with that, I'm talking about very high emission. We don't know where these processes become important above a low emissions pathway. So that's a caveat to keep in mind. The other thing is that I think has framed in the policy note, we are pretty confident that 2 meters is going to be exceeded regardless of emissions. But the range of when that could happen could be anywhere from 100 years to 2000 years, depending on emissions and depending on how unstable the ice sheets are.
Thank you. I think I have at this stage 2 last questions, which are pretty general. And I'm curious to hear your comments. So, for example, could you please remind what does 2 meter global sea level rise mean locally in Europe or in France, for example? So you can have some example in the policy brief, but maybe Gonéri or Robert, you want to give more details or other example. What does this mean, 2 meter sea level rise in Europe?
So I think if you want to see the impacts in Europe or elsewhere, you have to visit the web page that was mentioned by Bob Kopp. So the NASA web page, which is basically displaying the IPCC data, the IPCC projections. So in practice, it will depend when we exceed these 2 meters. So if it is in 2100, which would be very early, or 2120, then it means there will be a huge contribution of Antarctica. So presumably, the consequences for Europe would be a little bit more than 2 meters. But if this is farther in the future, then maybe this will come from a contribution from several contributions of sea level rise, like Greenland, glaciers, thermal expansion, and Antarctica. And maybe we would be closer to the global average. So it's really a question of time. When do we exceed these 2 meters? And what are the contributors to this sea level, to this global sea level of 2 meters?
And just following on, I mean, I think the timing is very, very critical, because if it's a very rapid rise in sea level, will essentially submerge things. So you're going to drown wetlands, beaches, etc. If we have a slower rise, that does give more time for things to adjust. It gives more time for nature-based approaches to work. So we might, so over the, if it happens over the sort of 2000 years, it will, maybe we can sustain our habitats, etc. Even though it's a big change, because it happens slowly, the systems can adjust to those changes, particularly maybe with a little bit of help from people where maybe they're not quite able to. So, I think the timing, the rate at which it happens is very important.
Somehow question related. How do you propose public policy implementation to enable sea level adaptation? That's a big question.
Could you repeat the question, please? I'm
How
sorry.
do you propose public policy implementation to enable sea level? How you promote, I guess, public policy implementation to enable sea level adaptation?
Well, I think things like the IPCC policy, I mean, I think making information available and trying to, which is what we're trying to do in the policy brief, and giving practical things that people could do. Because I mean, the wheel, the second diagram, I sort of went through over very, very quickly, so you can look at it in more time. There's a lot of practical guidance there, and obviously the policy brief itself is expanding on that a little bit. And I think it's getting people to engage with the fact that sea level is rising and something needs to be done. That's probably the most fundamental. I think many people still in their mind, not the people on this call, but when you go out to the people in the street, don't fully, even though they see it on the news, they do not fully get the size of change that's coming, and hence the need to do things differently. And so I think you need to embed that in the policy and the political process, and that's what's needed to really take things forward. And so that's an ongoing process. I don't think we ever stop doing that, because that need for education and communication will continue.
And if I may, I think there is a very important thing that needs to be sustained over time, which is international cooperation, because we see that no country is currently having a coastal adaptation policy that covers all topics, from chronic flooding to storm flooding to erosion to permanent submersion over time. And so international cooperation is really key to get the best out of the different experiences. And so, for example, this forward-looking approach that Robert mentioned from the UK and the Netherlands, but also this chronic flooding adaptations that we see from the US, maybe some experiment on nature-based solutions like we have on the Coastal Conservancy Agency in France and in other countries. And this, I think, is really important to make sure that coastal adaptation is progressing.
Okay. What are our actions to reduce snow melt in Antarctica, and how to fix eternal snow so that it can return to normal again? Bob, you want to answer, or shall I enter into the dance?
I mean, I guess I can. Well, so first of all, I would say that actually snowfall in large parts of Antarctica is increasing in a warmer climate with a moister atmosphere. So parts of Antarctica are gaining mass. The loss of ice from Antarctica is driven by what's happening on its edges. It's the flow of ice into the ocean, not melting or net decrease of snowfall. That's the issue. And I think the basic answer is what you should do is not warm the planet up more. And Gaël, if you want to, other people on Protect who also work on this issue, I'd be happy to turn it over to them. There are some French notions about engineering approaches to putting more ice on the continent.
I'm not sure I want to further discuss this solution, but regarding how to go back, I think so I agree with you. Antarctica, in scenario with a warmer climate, there is more snowfall, and the loss of Antarctica is not related to a decrease in the snowfall. But however, if we look at mountain glacier, for example, they are retreating, and they will continue to retreat. And basically, in a warmer world, there is less ice. And so if we want to come back to what we have known for the 20th century, we would have to stop emitting CO2 and decrease the amount of CO2 we have into the atmosphere. Okay, there are some very specific questions related to erosion and sand pumping. I don't know if the audience has the answer, but let's try. Who decide where to do and where to not do sand pumping? I don't know.
Well, I could chip in. I mean, I suppose, I think, if I'm understanding it, they're talking about the notion of beach nourishment. This is the question. This is what I'm going to answer. And I mean, like in the case of the Netherlands, they have outlawed coastal erosion. So in the sense, in the Netherlands, by that law, where there's erosion, sand is pumped. But I think in most countries, there's some kind of notion, a lot of countries, there's a notion of cost-benefit analysis, that if you're going to nourish a beach, that the benefits need to outweigh the cost of doing it. So that implies you do it in places that are developed. So you don't do it, that's been the traditional sort of approach. So there is some kind of economic rationale for making these decisions. So it depends on the context. I mean, you know, if you have a law that says your coast can't retreat, you might do it everywhere. If you, in other places, it's probably more sparing, should we say, where you think the benefits are the largest.
Okay, thank you. Again, extremely specific. Would the modelers be willing to rerun the regional model of the Mediterranean to properly assess the sea level rise under the various scenarios, including the Nile flow cessation since 1965, from million cubic meter to merely 5,000 cubic meters per year, and a large flow from the Suez Canal? So I don't know if this has been taken into account, and does anyone has a specific answer to this very specific question?
I don't have a specific answer. One thing I was to say, of course, the role of the IPCC is not to run models, it's to assess the literature, right? And so the question is not really properly directed to the IPCC, but rather people who run regional ocean models in the Mediterranean. The one thing I can say from the perspective of the IPCC is that if you think there are processes of that scale of atmosphere-ocean dynamics that are important, and we do know from the literature that certain fluctuations in how much fresh water you add, for instance, off the east coast of the US during wet seasons versus wet years versus dry years does affect sea level on a year-to-year time scale. You do need a more detailed study than in the IPCC sea level projections. The IPCC sea level projections are focused on sort of 20-year average sea level, and the atmosphere and ocean dynamics are coming out of global models that typically have a 100-kilometer resolution. And so particularly in sort of semi-closed basins like the Mediterranean, there is a lot of things that are not going to be picked up by those processes. Certainly on the year-to-year timescale, which the sea level projections from the IPCC don't attest to dealing with.
If I may, there are currently two groups working with high-resolution sea level rise projections in the Mediterranean. One is Mercator Ocean, which is operating the Copernicus Marine Service, and the other one is INIA in Italy. So probably there are others, but at least those groups I know. And okay, basically, one of the problems is that Mediterranean Sea is losing more water than it gains from rivers. So basically, there is water entering through the Gibraltar Strait, and then there are the gravitational effects associated to mass losses. So today we have, in fact, some projection from the Mediterranean. You can see them in the cross chapter paper 4 on Mediterranean Sea in the working group 2, but there is still a lot of research to be done in this area, as Rosh, Bob was telling, and this group should be able to deliver some high resolution projections in the future.
Okay, thank you for this answer and precision on sediment. I have maybe the last question, or it can be a nice last question. Considering the time and resources it takes to imagine new human-made structure to protect inhabitants, isn't it too late to start thinking about those solutions? Rephrased, shorter, is it too late to start thinking and building things to protect our coast against sea level?
I think in the short term, I would say not, because the time scale of building dikes, etc., you can build a dike quite quickly. I mean, I guess if you want to build them, it's the scale at which you wish to do it. If you wanted to build dikes around the entire coast of Europe, that would probably be almost impossible. But I think probably we're talking about targeted protection of certain areas. That is much more feasible. And we've been doing it for a long time, so we know how to do it, and we have the techniques, etc. Barriers and things like that take a bit longer, but the Thames barrier took 28 years from a very big flood that kind of made people wake up to it being commissioned and operating in 1982. So I think there is time to build protection now. I think the question probably is that the smart thing to do? And when we look at the adaptation pathways point that Marjolijn was presenting, if we build a defense today, that will work for a period of time, depends on how fast sea level rises and other issues. And then it will need to be upgraded, or we'll have to move to something else. And I think that's the point to think through. And, you know, can you just keep on raising? In some places, probably yes. In other places, that may not be wise. And so I think it's thinking through those longer term sort of sequences of options and recognizing that, I suppose if you step back, we are bequeathing to our children and grandchildren choices and things to do. And so, so recognizing that and not just blindly doing it, but trying to do that with a little bit of forethought, so that we leave the place in maybe a slightly better place and give them more options. That's all.
Thank you. I think I asked all the questions, not all the comments in the chat, but I may have missed some. Maybe.
Can I chip in, Gaël?
Yes, please jump in.
I think there are several questions about coastal erosion. So basically, we've been discussing a lot about flooding, but not a lot about erosion. And since Rosh Ranasinghe is here and he's really an expert in this area, he was in working group 1, maybe he can explain what is our current state of knowledge in this area.
Mm-hmm.
Are you here, Rosh?
I fear he left.
Okay, he left, sorry. Then I think I can explain a little bit.
Sorry, I had some problems.
Okay, Rosh, here you are.
Sorry, I had a bit of a problem there. What was the question again? Sorry.
The question was, so we have been discussing a lot about flooding, but of course erosion is another threat due to sea level rise, and especially because there are interactions between flooding and erosion. Once you have removed the dune, this may enhance flooding, and also because it represents already a severe concern in some regions, like for example France. And so maybe you can give us a little bit of ideas where we are in terms of assessing the impact of sea level rise to coastal erosion. What is the state of knowledge in this area?
Yeah, well, that's something that I have been working on for quite some time, and it's also a bit of a contentious area. I do think that, especially with the tools that have been developed over the last, modeling tools that have been developed over the last decade or so, that we can do a pretty good job of assessing coastal erosion due to climate change at the local scale. I mean, of course, there's still a lot of uncertainties, but we can also quantify those uncertainties. But once we start going beyond the local scale, then we have to, of course, make some simplifying assumptions, and it's a very non-linear process. You know, very local features like the geomorphology of the area and sediment supply from rivers, everything comes into the sediment balance. So yeah, at this point in time, I think it's practically impossible to continent scale or a global scale assessment with a very high level of accuracy. But still, as some of you would know, there have been some attempts to do some first pass attempts just to kind of give ideas of where you might get more erosion than other areas. So I think those kind of estimates are still useful to prioritize areas that you want to look at. But yeah, a lot of people are still working on trying to improve the ability to have regional to global scale projections of coastal erosion due to climate change. I hope we will meet some success soon. Thank you.
Thank you. We received a question on Twitter. So how will different emission scenarios affect storm tracks and storminess, and how could change in regime influence our response? I guess, not sure to fully understand, but I guess that, yeah, how the storm tracks could change our projection sea level and how it changed from one scenario to another. Bob, maybe you have an answer.
Yeah, sure. I mean, I think it's less how it changes our projection of sea level, more how it changes our projection of coastal flooding that is amplified by both sea level and storm surge. And that is an important question. There's pretty good agreement with respect to hurricanes that the intensity of hurricanes is increasing and will increase more under higher emissions scenarios. The details of how that translates into the distribution of storm events or storm-related flooding is complicated, and I think there's not a great deal of agreement on track shifts at the moment. But just to point to one work in the New York City area suggests that actually track shifts and the intensification of the storm sort of work in opposite directions, because while you're seeing more intense hurricanes, they actually seem to be fewer that pass right near Battery, at least in some of the models. I don't think there's enough models to have a great deal of confidence in that finding. But I think that the basic point that at sort of a larger scale, you expect to see more intense hurricanes. It's still ambiguous what we would expect to see in terms of the overall number of hurricanes, and track shifts certainly matter for that. How fast hurricanes move. Now, I'm in North America. I mean, hurricanes are more of a concern here than in Europe, although you do see them there too. Like the literature on extratropical cyclones, which we call nor'easters here, I think is even more ambiguous in what the terms of changes would be.
Thank you. So
can I just chip in?
Yes, please.
Because I mean, tomorrow is the 70th anniversary of the 1953 storm surge, which killed 307 people in England, 19 in Scotland, over nearly 2,000 in the Netherlands, and about 50 people in Belgium. So it was a very large disaster. And I suppose I'm not sure this is in the IPCC, to be honest, but I just thought it was just a comment about what somebody called grey swan events, where people were doing some modeling of what might, this isn't climate change, it's looking at what might happen, and just playing with North Sea storm surge models, and they concluded that there could be an event a meter bigger than we've seen under current climate conditions. So it's when you're thinking about the storms, there's the effect of climate change, but also there's the, are you unlucky? And one of these grey swan events comes along. So so I think that's always something. There's many degrees of freedom with the problem we're discussing here, I suppose, or several degrees of freedom.
And if I can complete also, in the IPCC report, in the working group 2, there is a cave hit, so an emerging evidence from some literature showing that by 2100, under low adaptation and high global warming, coastal events may be sufficiently large to cause failure in the insurance and the bank system and create basically a systemic crisis, actually. So this is something that can happen. We cannot exclude. It's a little bit like the Antarctica ice sheet collapse. So we don't say it will happen, but it could happen. It cannot be excluded, and this is something we should keep in mind, I think.
Okay, thank you. So I think I asked all the questions I read. I apologize if I missed some. I would like to finish by a general question to you. It's not so often that we have so many co-authors of the IPCC around the same table. So what are for you the next challenges regarding sea level science? Maybe one or two bullet point each, or?
Sure. I can give a couple. So on the physical science side, I mentioned that our projections are focused on sort of longer term, like trends, and are based on sort of global scale models. I think on the projection side, I think there's a lot to do on sort of shorter timescales, higher spatial resolution that have to do with with natural variability and the way natural variability changes under climate change. I also think a lot of the interesting questions are actually in the working group 2 domain. And I mentioned our project MOC, which is really focused on these feedbacks between changing coastal hazards, how that affects decision-making by individuals, how that affects decision-making at a government level, and the ability of things like, local and regional governments to provide services, and how those feedback upon the efficacy of adaptation pathways, like Marjolijn was talking about. So very much like, there are some basic science questions, but I think a lot of the interesting ones are actually at the interplay of the changing human system and natural system and the dynamics there.
So if I can continue for working group 2, I think that today we see that when you look at the working group 2, you can see that in the end of this summary for policymaker, the summary for policymaker is not only speaking about adaptation, but about climate resilient development, which is actually the combination of 4 actions. So limiting climate change, adapting to climate change, reducing biodiversity losses, and achieving the sustainable development goals. And I think we have seen today that there is not a single future for coastal zones. There are many potential pathways leading to different coastal area. So maybe heavily protected coastal area for some urban area, maybe some area where we can see more coastal ecosystems and maybe some relocations. But there is not a single future. And what is not clear either is what means climate resilient development in coastal zones. And for this, I think we need to have a broader picture. So something considering both the working group 2 and working group 3 outcome in order to have in mind a picture of what could be coastal resilient area.
Thank you.
Well, if I carry on then, so I think I agree very much. I think the interface between working group 1 and working group 2, and sort of, if you like, the physical science interacting with the human system is very fundamental, and there's a lot that we're only beginning to investigate that at the present time. We've tended to see it as separate, and I think really the outcomes that are important emerge by the sort of co-evolution of those 2 systems along these pathways. But I suppose, and on a more sort of nitty-gritty way as well, also, I think communicating climate science coastal science to coastal practitioners, I think there's a lot of work in really understanding adaptation and what information will actually lead to better decisions. So it's kind of I think that that area is somewhere where a lot can be done. And I think that probably builds on and reinforces what the previous both speakers have said, actually.
Okay, if I can add to that, I think in addition to like working group 1 and 2, I would like to add working group 3 as I think adaptation and mitigation should go hand in hand. And we need to look at the synergies between the two and avoid the negative interaction, so to say. And I guess in addition, like if you focus on working group 2, linking the short-term adaptation needs with the long-term potential adaptation needs, the developments that take place, the other challenges and crises that we have already nowadays, I think is very important, also considering the amount of time that we need for planning and adaptation and the path dependency. So I think it's still a lot to do, but maybe let's also finish that we already know a lot about impacts and adaptation. So even despite these uncertainties, or maybe because of these uncertainties, already a lot of decisions can be taken now based on the current evidence and knowledge that we have.
Thank you. This sounds to me as a very nice conclusion. So I would like to warmly thank all the speakers for the preparation of the slides and their time. So thanks a lot. And as mentioned, the materials proposed here will be gathered together and published on the Protect website, and you will be informed by email. So with that, we will close this webinar. Thanks again. Thanks for your time all, and wish you the best for today. Enjoy your day. Goodbye.
Thank you. Bye-bye.
Thank you.